Hello everyone. In this video, we will begin to discuss the topic of standing waves, section 4.5. In particular, we will understand the nature of standing waves. Standing waves are waves produced by the superposition and interference of multiple waves in which the amplitude of oscillation depends on the position. A way of thinking about this definition is that this part is how the standing wave is produced, and we'll get to that in a moment. The nature of the standing wave is bound up in this part of the definition, that the amplitude of oscillation depends on the position. What this means is that in a standing wave, the size of the oscillation will depend on where you are along the wave. So, if I play this simulation of a standing wave here, what I can see is that there are points along sort of my string that's shown as sort of that middle bar in the simulation, points along that string that have very large oscillation or maximum amplitude oscillation, and then points along the string that have less than that, and points along the string that have no oscillation at all, or that aren't oscillating. These points, the points that aren't oscillating, are known as nodes. Those points are points along the standing wave that, as we'll see, have perfect destructive interference, and as a result, do not oscillate. The x's mark points along the position of the wave where there are antinodes, and those occur at points of perfect constructive interference, as we'll see in a bit. The wavelength of the standing wave is shown by, per usual, points in phase. So remember that a wavelength is the shortest distance along a wave between two separate points in phase on the wave. And so this point right here and this point right here are at the same point along the waveform, and therefore represent a single wavelength. Notice that each point along the wave itself comes back to this equilibrium position. So, if we were to compare standing waves versus traveling waves, we could do so using a number of different properties. With respect to energy transfer, traveling waves transfer energy in the direction of propagation. So if you have a standard traveling wave and it moves, it will end up transferring energy in that direction of propagation, whereas a standing wave does not transfer energy from one end to the other. Although there is interchange of kinetic and potential energy within the standing wave. So very consistently, kinetic energy is converted to potential energy at every point along the wave. For a traveling wave, all particles have the same amplitude. But for a standing wave, the amplitude varies within a loop. By the way, a loop is this thing right here. So if this is our basic structure for a standing wave, then a loop would be sort of this shape right here. And the amplitude would vary within it. So you would find points with zero amplitude at the nodes, a point with maximum amplitude right here and here at the antinodes, and points anywhere in between. One thing to note is that within a wave, for a traveling wave, the phase within a wavelength is different for each particle. So if I have a particular wavelength, the phase for this particle right here is different than this particle right here, and this particle right here, and so on and so forth. Whereas within a loop, all of these particles are all oscillating up at the same time. All of these particles are oscillating down at the same time. As a result, adjacent loops are exactly 180 degrees or pi out of phase. With a traveling wave, the wave profile or envelope or shape propagates in the direction of the wave at the speed of the wave, whereas in a standing wave, the shape of that wave stays put. It stays in the same place. We're first going to focus on the production of standing waves in strings. Okay, you can see a diagram of a setup that would produce standing waves in strings. We have a vibration generator here, powered by something sending it a signal. That signal generator produces oscillations at the point of contact with the vibration generator that are simple harmonic. So this vibration generator is vibrating up and down with simple harmonic motion. The result is a very clean standing wave, where at any point the wave is in either this position or this one, and you can see the antinodes and nodes labeled. You can find standing waves in strings in any kind of stringed instrument. So we'll focus in on guitars and violins and such, but any instrument that produces sound using strings tends to use standing waves in those strings to do so. We will model most standing waves in strings as having fixed ends, which, as we'll see, produce nodes on both ends. This is true even though the vibration generator here is moving up and down. The amplitude of the actual vibrations generated by that vibration generator, though, is very small compared to the amplitude reached by the standing wave. The vibration generator moves up and down just a little bit, whereas the middle point of the antinode moves up and down quite a bit. And fundamentally, and we'll discuss this in the next video, these standing waves in strings are produced when an incident wave, a wave coming from the vibration generator, interferes with a reflected wave coming off the boundary. And all stringed instruments produce notes this way. In the next video, we will discuss how those two waves interact.